Hi, welcome to our continuing study of Newton's laws. Today's topic, circular motion, is often presented in many textbooks as a separate chapter from Newton's laws, but it is really just an extension of motion and Newton's laws studies. In fact, it was Newton himself who offered us the insight that we're going to use today to do some circular motion problem solving. But if you think about it, I think you'll realize that circular motion is just another form of two-dimensional motion. And so sometimes circular motion is actually introduced in the 2D kinematics section. But we're going to tackle it here in Newton's laws. Let's get started. Let's take a look at the example on the screen. It's a car moving in a circle, like a circular track at a constant speed. Now you know from Newton's first law, okay, objects in motion stay in motion in a straight line at constant speed unless acted upon by an outside force. You know from Newton's first law that this car, since it's not moving in a straight line, must have an unbalanced force acting on it, right? It can't naturally, all by itself, move in a circle. So we know that since it has an unbalanced force acting on it, it must be experiencing acceleration. But here's the problem. We've just stipulated this car is moving at a constant speed. So if we try to tackle this problem with our traditional understanding of acceleration, okay, it might seem at first that we fall short, because if we try to calculate the acceleration of the car that we know that it must have, notice what we do here. It's v final, 30 kilometers an hour, minus v initial divided by some time period, right? Say if we look at the car from where you see it right there, and then at some later point, right? That would be some time around the circle vf, like right there, versus vi. So if we try to calculate acceleration for that time period, we're going to come up with 0 as an answer, right? Because 30 minus 30 is 0. So the way out of this conundrum is to recognize that the acceleration equation is actually in vector form, right? And when we subtract two vectors, okay, we can only subtract their magnitudes, right? We can only do 30 minus 30 if they're in the same line, right? And you can see here that they're not in the same line. So it turns out that this acceleration equation still holds, but you have to do the vectorial subtraction rather than the scalar subtraction, right? Scalar would just be 30 minus 30. So I'm going to come down and I'm going to draw that for you. Remember that when you subtract two vectors, it's like adding a negative. So what we're basically doing is we're taking this vector here. Okay, let me use the arrow. We're taking the v final vector, okay, and we're subtracting it we're subtracting vi from it, which is like adding the negative of vi. So that's going to look something like this. It's going to be like plus, right, this is vf, plus negative vi, which is going to be going the opposite way, right? That's negative vi right there. So if you put those two head to tail, there's vf, and then at the end of it we'll put vi, okay, like so. All right. You can see what the resultant looks like. The resultant is going to kind of point that way, okay? Now I didn't do it perfectly, but you should see that the resultant actually points toward the center of the circle, right? So this resultant here, which we can label as delta v, points toward the center of the circle. That gives you an idea of the direction of acceleration. Hopefully that's familiar to you. An object moving in a circle experiences an acceleration toward the center of that circle, and that acceleration is called centripetal acceleration. Back to what Newton gave to us. What Newton did is he came up with a new expression, a new version of this equation that we can use for circular motion. Okay, the derivation of it, he used it when he was studying planetary bodies, but the derivation of it I'll save for your own perusal in the textbook. Here's what he came up with. Centripetal acceleration is equal to the square of the velocity around the circle divided by the radius. Okay, so that's an equation that you're actually given on the AP test. All right, so you don't even have to memorize it. It's a very nifty little equation. It applies to objects moving in a constant speed, right, in a circle. So notice there that if you turn a tighter circle, right, you know from experience that you're going to experience a greater force. That means you're experiencing a greater centripetal acceleration, right? If you make the radius smaller in this expression, you see that's true. Okay, and then of course if you drive at a faster speed, obviously you're going to experience a greater acceleration as well. So those two quantities are the ones that centripetal acceleration depends on. All right, so that's what Newton offered to us in his study of planetary motion for objects moving in a circle at a constant speed, right? So this is going to apply for any object moving in a circle, satellite, moon, whatever. All right, let's look at circular motion in a more general sense. Okay, things aren't always moving in a perfect circle. So more generally speaking, if we have an object here that's moving along a curve, right? Some of it is circular, some of it is just kind of curved. We actually have two types of acceleration. Okay, so let me draw some arrows for you here. That's the instantaneous velocity right there, right? So I was tangent to the curve at that point. And so it turns out that an object moving in a circle can have two types of acceleration. It can have the one that you've already been told of. That's the centripetal, or it's also called the radial acceleration. Okay. There is, however, another type of acceleration that's possible, and that's if the object is slowing down or speeding up as it's going through the circle. Remember, in the previous screen, we were looking at the car and assuming that it was keeping a constant speed the whole time. But in real life, right, when you're turning or when a race car is turning in a race, it's going to be speeding up or slowing down in the direction of motion. So let's switch colors here. We're going to call that tangential acceleration, right? So I'm going to draw an arrow. It should be right on top of the velocity arrow. I'm going to label it AT for tangential acceleration. Maybe just to be consistent, let's come back here and make that green as well, just to separate the acceleration from the velocity. So the tangential acceleration combines with the centripetal acceleration to yield the total acceleration. So you can see in this case that, and I'll use a resultant, the actual total acceleration is something like in that direction right there, right? Because it's the combination of the centripetal and the tangential acceleration. So you can see that those two are perpendicular to each other. If you wanted to find the magnitude of the total acceleration, then you could use a Pythagorean theorem, right? The magnitude of the total acceleration is a centripetal squared plus a tangential squared square root, right? Pythagorean theorem. That will give you the total acceleration anytime for an object moving in some sort of generalized circular motion. There's a special type of circular motion, okay? A special type of circular motion that we abbreviate UCM, right? Uniform circular motion, okay? Uniform circular motion. It is a simplified form of circular motion. It's nifty, okay? And it's the type of motion when you have no tangential acceleration, okay? In other words, when you're moving at a constant speed. So you could write that like this, AT equals 0, okay? And when that's true, that's when this expression holds, okay? This centripetal acceleration expression. All right, let's take a look at the next page. Wherever there's an acceleration, right, Newton's second law, there's a force, okay? And we're going to call that force the centripetal force. If we come back to the car moving in a circle, underneath I've drawn the side view, right? How it might look from if you're standing right on the road, okay? Let's draw a free body diagram of the car moving around the circle, okay? Let's say it's a flat track. And your usual suspects are there, okay, like this. That would be, of course, the normal force, and that would be the weight. And since it's moving in a circle, it must experience a force moving toward the center of the circle, okay? And that's the force that keeps it moving toward the center of the circle. Do you know what that force is? That's right. It's the friction force, right? If there's not good traction between the tires and the road, this is not going to happen, right? The car's going to slide out. So in this case, the friction force is acting as a centripetal force. Notice that the centripetal force isn't a new type of force, okay? You're never going to do a free body diagram that looks like that, right? F centripetal. That doesn't exist. It's the forces that we're already familiar with, friction, normal, tension, weight, acting toward the center of a circle, causing an object to move in a circle. So you still always label it the way you always have, but you want to recognize which force is acting or which forces are acting as a centripetal force. Okay, so if we go to our list here, okay, this is our list of forces we've been working with all school year. Any one of those soar in a given situation or a combination of them could work to move an object in a circle. And when they're doing that, they're called centripetal forces. One interesting special case is the situation called the banked curve. Okay, this is the kind of track that you see in NASCAR racing. And the reason that is because, let's draw the free body diagram here quickly. Okay, you still have weight down, and then you have the normal force, okay, like that. And basically what ends up happening is that when you bank the track, okay, let's take this normal force and break it into its components, right? It has a horizontal component and it has a vertical component, right? It turns out that that horizontal component right there pushes toward the center of the circle, right? And I've missed friction here. Friction's going to be, depending on how fast you're going, and we'll talk more about this next time, but friction could be acting this way, so there's a component of friction toward the center. So bank curves basically provide an additional force toward the center of the circle besides friction, right? On a flat track, it's just friction keeping a car moving in a circle. But on a bank curve, there's that additional normal force pushing toward the center as well. And that provides an additional center-seeking force, therefore allowing the car to achieve a greater speed. Next, we'd like to tackle a point of great confusion when it comes to circular motion, and that is the concept of centripetal with a P versus centrifugal with an F. For some reason, students love the centrifugal force. Whenever I'd ask for an explanation, I always hear about centrifugal forces when I talk about circular motion. But it turns out that the F in centrifugal, right, the F right here, stands for fake. Not really, but it's a good way to remember that the centrifugal force is what we call a pseudo force. It's a force that appears to be there, but really isn't. Okay, let's go back to the car moving in a circle. Down in this position here, okay, this is the position of your body, right, straight up before you hit the curve. You know that when you hit the curve, your body is now tipped that way, right? It's like you're leaning to the outside of the circle. So it seems like the force is pushing, there's a force pushing you to the outside. But when in reality, you know that when you're turning in that circle, right, the force is toward the center of the circle. The actual force is opposite what you think it is from your perspective. Okay, let's look at another example when this comes up. If you're in a bus, right, and you are holding something suspended from a string like this pendulum bob here, you know that if you accelerate, it's going to lean back, right? So from our perspective in the bus, it would seem like some force is pushing the pendulum back. But which way are we accelerating? That's right, we're accelerating the opposite way, right? So the force on the bob is actually to the right, though from our perspective, it feels like it's from the left. Here's the reason for all of that. In the bus and in the car, you are not in what's called an inertial reference frame. You are in a non-inertial reference frame, right? And in a non-inertial reference frame, which is simply one that's accelerating, Newton's laws don't hold. So that's why so when you're looking at something from a non-inertial reference frame, things are going to look different. In fact, they're going to look opposite. So the centrifugal force is that fake force that you feel pushing you to the outside of the circle, when in reality, you're being pushed to the inside. Last thing today, as usual, is we want to make this applicable to building our skills in problem solving. So let's take a look at a problem. Okay, next page here, example problem. This is an example of a tether ball. I'll give you a moment to read it. Actually, you might want to pause it and read it. So I'm going to go ahead and draw this out for you. Okay, there you see a sketch of the problem. I still see a lot of people trying to skip the most foundational step of problem solving, and that is the free body diagram. I come over to help you out. I look at your page, and I see chicken scratch and formulas and numbers, but I don't see a free body diagram. The free body diagram is the conceptual foundation for problem solving. So you've got to make sure the free body diagram is correct here. See if this makes sense to you. Okay, we get the weight down, right, and we have the tension of the string like that. Okay, hopefully you can see the combination of those two is going to produce a force, in this direction here, okay, toward the center of the circle, right? So it's the combination of tension and weight that act as the centripetal force. Actually, I said that wrong. It's the horizontal component of tension that acts as the centripetal force. So there you have it, and you're going to proceed very much like you did before. Okay, I'm going to go to the next page for the sake of space. But basically, you're writing F equals ma in each direction again, okay, like this, and proceeding, like I said, much as we usually do. Let me go back here. I want to do one thing. Let me remember for any force that doesn't line up with our coordinate axes, okay, we have to break that into horizontal components that do, horizontal and vertical components that do, right? So this would be tension broken up into T, Y, and T, X, like that. So the only difference is that for the direction that's experiencing centripetal motion, right, which in this case is the horizontal, we're going to replace the A, okay, right here with the v squared over r. That's really the only difference. Okay. On the y side, it's unchanged because there's no circular motion on the right side. In fact, it's not even moving up and down as we go to the right. It's not moving up and down, so there's no acceleration in that direction. I leave it to you to solve this problem. Okay, solve for the tension and the speed of the ball. There is one more nifty formula that comes up. You're not going to need it in this problem, but it comes up often in circular motion problems, especially planetary motion. And that is this one here, your very simple distance over time equation. But when you're moving in a circle, right, the distance you carve out is the circumference. Okay? And the time that it takes to go around the circle one time is called the period, which we use capital T for. So it's this formula here that you'll see a lot that comes in handy, like so. Okay, so keep that one in mind. It's not one that's given to you. It's one you would be expected to derive. That's it for circular motion problem solving. Thanks for your attention. We'll see you in class.